Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. My name is Dr. Farhat Mahmood, and now we are back with our second lecture of our third chapter of X-ray diffraction technique under the course code of CHEM5134. This lecture is the continuation of the previous lecture 3.1, and we will discuss the next slide of the remaining lectures coming in this. So here we have a figure which is showing part of a single crystal X-ray diffraction pattern. Here individual spots arises by the diffraction of X-ray scattered beam from different planes of the atom within the crystal. So such kind of spots that occurs on the detector or the film is known as diffraction pattern, and by using this diffraction pattern we get detailed information about the structure of the crystal or crystal lattice. The position for most atoms, including carbon, nitrogen and oxygen, and metal in most inorganic compounds can be determined with the sufficient accuracy that bond length can be defined to within a fraction of a picometer. As an example, the sulfur-sulfur bond length in monoclinic sulfur has been reported as 204.7 plus minus 0.3 picometer. Note: Note on good or at least conventional practice, crystallographers still generally use the angstrom. 1 angstrom is equal to 10 raised to power minus 10 meter, or equal to 10 raised to power minus 8 centimeter, and it can be written as 10 raised to power minus 2 picometer as a unit of measurement. This unit is convenient because bond length typically lies between 1 and 3 angstrom. The sulfur-sulfur bond length in a monoclinic sulfur would be reported as 2.047 plus minus 0.003 angstrom. And the position of the hydrogen atom can be determined for inorganic compound that contains only light atoms with atomic number less than about 18, that is argon, but their location in many inorganic compounds that also contain heavy atoms such as the 4D and 5D series elements. This can be difficult or impossible. The problem lies within the small number of electrons on an hydrogen atom, just one, which is often reduced even further when hydrogen forms bond to other atoms. Other techniques, such as neutron diffraction, can often be applied to determine the position of hydrogen in inorganic compounds. Molecular structure obtained by the analysis of single crystal X-ray diffraction data are often represented in ORTEP diagram. Following figure ORTP OAK ridge thermal ellipsoid program. So this is the figure representing the ORTEP diagram of cesium oxalate monohydrate crystal CS2C2O4 with water molecule monohydrated. The ellipsoid correspond to a 90% probability of locating the atoms. This is a software which is used in the computer to depict the position of the different atom present in a single crystal. In an ORTEP diagram, an ellipsoid is used to present the volume within which the atomic nucleus most probably lies, taking into account its thermal motion. The size of the ellipsoid increases with temperature and, as a result, so does the impression of the bond length extracted from the data. The advantages of this ORTEP diagram are of this analysis of diffraction pattern. The analysis of diffraction pattern obtained from single crystal allows full determination of the structure. Here is about some explanation about ellipsoid. An ellipsoid is a three-dimensional closed geometric shape, all planar sections of which are ellipses or circles. An ellipsoid has three independent axes and is usually specified by the length A, B, C of the three semi-axes. If an ellipsoid is made by rotating an ellipse about one of its axes, then two axes of the ellipsoid are the same, and it is called an ellipsoid of revolution or spheroid. If the length of all three its axes are same, it is a sphere. Then it is known as a sphere. Dear student, now we are going to discuss the procedure of single crystal X-ray crystallography. Here are three basic steps. The first step is that in this step this step is first and it is often most difficult step is to obtain an adequate crystal of the material under study. That means in this step we have to obtain the adequate amount of the crystal that we have to study using this technique. The crystal should be sufficiently large, typically larger than 0.1 millimeter in all dimensions. It should be pure in composition and regular in structure, with no significant internal imperfections such as cracks or twinnings. So here is the first step in which we have to obtain a crystal of an appropriate size and with pure composition and regularity in its structure and with no significant internal damages such as cracks in the crystal. And in the second step, the crystal is placed in an intense beam of X-rays, usually of single wavelength. That means the X-rays that is coming from the X-ray tubes, these are passed through the monochromator, and after passing that monochromator, it contains only single wavelength and it produces the regular pattern of reflection. As the crystal is gradually rotated, previous reflections disappears and new ones appears. The intensity of every spot is recorded at every orientation of the crystal. Multiple data sets may have to be collected, with each set covering slightly more than half a full rotation of a crystal and typically containing tens of thousands of reflections. And in third step, these data are combined computationally with complementary chemical information to produce a refined model of the arrangement of atoms within a crystal. The final refined model of the atomic arrangement, now called a crystal structure, and it is usually stored in a public database. Interpretation of data can be done by using the following techniques. Typical mineral structure contain several thousand unique reflections whose spatial arrangement is referred to as a diffraction pattern. Indices like HKL, Miller indices, may be assigned to each reflection, indicating its position within the diffraction pattern. And this pattern has a reciprocal Fourier transform relationship to the crystalline lattice and the unit cell in real space. This step is referred to as a solution of the crystal structure, and after the structure is solved, it is further refined using least square techniques. This procedure is described fully on a single crystal structure refinement SREF. Here is a figure which is showing electron density map for NaCl. And in this electron density map, the electron density map describes the contents of the unit cells averaged over the whole crystal and not the content of a single unit cell. Moving to the next slide, here we see that an electron density map show a various variation of electron density throughout the unit cell. When solving an unknown structure, it is often useful to construct electron density maps, Fourier maps, in order to try to locate atoms. As the structure refinement proceeds, the quality of the electron density map usually improves and the background electron density decreases and more peaks due to the individual atom becomes resolved. The electron density map obtained at the end of the structure determination is an important piece of information. Electron density map take the form of section through the structure at regular intervals. By superposing these, a 3D picture of the electron density distribution may be obtained. In the above figure shown, the electron density distribution for a section through a very simple structure NaCl. This is essentially a counter map showing lines of equal electron density by the interpolation from the calculated electron density values at each point on the grid superposed on the unit cell. The section shown is parallel to one unit cell face and passes through the center of the sodium ions and chloride ions. It has the following features. An electron density map resembles a geographical counter map. The counter arise lines The counter are lines of the constant electron density throughout the structure. Electron density maxima correspond to atoms. The coordinate of the atoms in the unit cell are given by the coordinate of the peak maxima. The peak highest is proportional to the number of electrons possessed by the atom, which apart from very light atoms equal to the atomic number of that atom. In above figure, peaks of relative height 100 and 50 are seen and are assigned to chloride and sodium ion respectively. The atomic number of chloride and sodium are 17 and 11 for ions. The number of electrons are 18 and 10 respectively. The experimental maxima are therefore in fair agreement with the expected values, and the electron density map also show that our mental picture of atom as sphere is essentially correct, at least on a time average, and the electron density drops to almost zero at some point along the line connecting the pair of adjacent atoms in above figure, and in this supports the model of ionic bonding in NaCl. In structures which have covalent bonding, there is residual electron density between atoms on the electron density maps. However, in other than very simple structures such as alkali halides, it is difficult to use electron density map to determine the quantitatively the distribution of valence electron. In most structures refinements, both the position and temperature factors or thermal vibration factors of atoms are varied in order to achieve the best agreement between measured and the calculated structure factors. In refining simple structures, the atomic coordinates are usually known accurately, but in more complex structures, various kinds of local structure distortions are possible, which cannot be determined individually but are averaged in the final refinement data. The temperature factors allow for both local structures distortion involving small atomic displacements and also temperature-induced atomic vibrations. Dear student, in this slide we are going to discuss something about single crystal structure refinement, SREF. The electron density map generated by the solution of the phase problem can be seen as a basic structure map. However, the assignment of the atoms to different intensity centers is key to understanding the structure. The step of atoms assignment is referred to as solving the crystal structure, and the procedure can be mystifying to the beginner but is reasonably straightforward. There are two basic procedures for structure solutions which will be discussed below. One is known mineral. If the sample is a known mineral species, a template of a solved structure of that species may be used for initial atom assignment. And this speeds up the solution of the structure elucidation as the major site can be assigned quickly. Once these have been assigned, the solution can be further manipulated to extract a better agreement between the observed F observed and the calculated data F calculated. Typical steps include changing the site occupancy, splitting the site occupancy between two elements, allowing the sites to become anisotropic, and locating hydrogen. As the hydrogen is the lightest element, it can be difficult to locate in mineral with significant heavy element contents. So, small changes are made at each step and then run through least square cycles which recalculate the structure using Fourier transformation. Practiced refiners tend to follow the same step each time. And if the material is unknown, that is, if we have unknown mineral, more challenging is when the mineral is unknown or a new species. Here, a template may not be able to be used to, and elements must instead be assigned based on the geometry of the intensity, centers, and the chemistry of the material. This procedure can be much more difficult as it is often though trial and errors that the correct assignment is found. Once it has, the structure will be further refined as described above. And now moving on towards the results. The result of the structure refinement yield a list of atom X, Y, Z assignments in the unit cell. Shapes of the anisotropic intensity center for each atom, thermal parameters, and the distance of the nearest atomic neighbors. Additionally, the angle between nearest neighbors is also given. Quality of solution is assessed by the value of R1, WR2, and GOOF. R1 is often called the R value, is the agreement between the calculated and the observed models. The formula for this value is R1 is equal to S mod FO minus FC observed values, FO mean observed values, and FC mean calculated values. I divided by SFOI. Ideal solution would have R value of 0. However, due to the random errors, this is never achieved. The R value listed as percent of less than 5% are considered good solutions. High quality samples, which often result in R values lower than 2.5%, and WR2 is similar to R1, but refer to scared F values. This result in WR2 always having a bigger value than R1. The final value GOOF refer to the goodness of fits of the solution. In addition to the difference in F values, the GOOF also takes into the account the number of the observed reflections and the parameters used. At the end of refinement, the GOOF should be approach 1. The software that are used in the refinement of the structures are structure refinement is greatly aided by the software packages. Probably the most widely used packages of software is the Shell XTL program suite. The different program in this suite, including XP, REP, XP, and SHELXL, that allows for the initial solution of the phase problem, imaging of the crystal and the refinement of the structure. So here are the links that can be we can read about this software SHELXT tutorial, and there is another link which is giving information about SREF. So dear student, thank you very much for your patience for listening this second lecture about the single crystal X-ray diffraction. In the next lecture, we will continue the remaining portion of this chapter, and hopefully you will learn this and listen this video very carefully. And I suggest you to prepare this lectures for your exam in accordance with the preparation of the MCQs, because the exam that are going to be held this year that are not as it was taken before. Now the exam will be in the form of MCQs. So you have to prepare these all lectures in according with the MCQs preparation. So best of luck. Let's see you again in the next lecture 3.3. Till then, Allah Hafiz.